This is the EdExcel A-Level Maths Paper 3 covering the Statistics and Mechanics module, and it's from the sample papers. Question number 1. The number of hours of sunshine each day, Y, for the month of July at Heathrow are summarised in the table below. We've got the hours and the frequency. A histogram was drawn to represent these data. The category 8, which is less than or equal to Y, which is less than 11, was represented by a bar of width 1.5 centimeters and height 8 centimeters. For part A, we have to find the width and the height of the 0, which is less than or equal to Y, which is less than 5 group. First of all, we know that the area in a histogram represents the frequency. So, if we take a look at information given for part A, for the 8 which is less than or equal to Y, which is less than 11, we know that the width is 1.5 and the height is 8. And so, with a width of 1.5 centimeters and a height of 8 centimeters, we can therefore conclude the area A is equal to 1.5 multiplied by 8, which is equal to 12 centimeters squared. We also know from the question that the frequency is 8. And so therefore, where we have 12 centimeters squared, this will represent a frequency of 8. And so we can find out what 1 centimeter squared is worth. That will be 8 over 12, which is 2/3. So 1 centimeter squared represents 2/3 frequency. Now, what we need to do in this question is find out the width and height of the 0 to 5 group. So, if we consider the 0 to 5 group, going back to the question, we know that we have a frequency of 12. So, with a frequency of 12, we can find out the required area. So, if we have 8 for our frequency representing 12, that means 4 for our frequency will be represented by 6, and so therefore 4 plus the 8 gives the 12, so 12 plus the 6 gives 18. So we have 18 centimeters squared representing a frequency of 12. Now the question is, how do we find out the width and height given that we know the area? Well, there are an infinite number of possibilities which give us this area of 18 centimeters squared. So how do we find the correct one? Well, we can do that by considering the interval and the width. Here we've got an interval of 3, and here we've got an interval of 5. Now, if we pay attention to the width, which is 1.5, that's half of the 3. So what we can say over here then is the ratio of the interval to the width is 2 to 1. And that's because we have the interval to find the width. And so if we've got an interval of 5, the width then will be half of the 5, which is 2.5. And so therefore, the width is equal to 5 divided by 2, which is 2.5 centimeters. And now that we know the width, area divided by the width will give the height. The height is equal to 18 divided by 2.5, which is equal to 7.2 centimeters. The width is 2.5 centimeters. The height is 7.2 centimeters. Now for part B, we have to use our calculator to estimate the mean and the standard deviation of the number of hours of sunshine each day for the month of July at Heathrow. Give your answer to 3 significant figures. Well, here we've got a grouped frequency table, and what we can do with that is, first of all, find out the midpoints. If we find out the midpoints of each of these intervals, we've got 2.5, 6.5, 9.5, 11.5, and 13 for our midpoints. We've got the frequencies, and if we go to our calculator, going to the statistics section on our calculator, press number 1 for one variable, make sure the frequency is on, so for that press shift, then menu for the setup, then number 3 for statistics. We want the frequency to be on. So for X, we type in these midpoints, so we've got 2.5, 6.5, 9.5, 11.5, and 13. For the frequencies, we've got 12, 6, 8, 3, and 2. Then press options, then one variable calc. Our calculator calculates for us the mean and the standard deviation. So for part B, from the calculator, the mean, we'll call it X bar. Rather, because we've got data involving Y's, Y bar is equal to 6.63, and that's given to 3 significant figures. And for the standard deviation, we need to use sigma X, or in this case, sigma Y, for the standard deviation. That's 3.69, given to 3 significant figures. Now, for part C, the mean and standard deviation for the number of hours of daily sunshine for the same month in Herne are 5.98 hours and 4.12 hours respectively. Thomas believes that the further south you are, the more consistent should be the number of hours of daily sunshine. You have to state giving a reason whether or not the calculations in part B support Thomas's belief. First of all, we know that Herne is further south than Heathrow. Now, what we need to do in this question is think about the data we've been given. We've been given data for Herne about the mean and standard deviation. So, we know information about the mean and standard deviation for both Heathrow and Herne, and that's shown here. The mean is 6.63 and the standard deviation is 3.69 for Heathrow, and for Herne the mean is 5.98 and the standard deviation is 4.12. So what do we notice about this? Well, we see that the mean is higher for Heathrow than for Herne, and the standard deviation is smaller for Heathrow than for Herne. And because we are considering consistency, let's focus on the standard deviation. So it's less consistent for Herne. And if we think about what we're actually measuring here, we're looking at daily sunshine, and Herne is further south than Heathrow. That's thinking about the locations in the large data set. So we know then Herne is further south, and so therefore we can see then the claim is not supported. If we're thinking what this person is saying, Thomas is saying the further south you are, the more consistent should be the number of hours of daily sunshine. We've shown that's not the case, because even though Herne is further south, it doesn't have the consistency, because its standard deviation is larger than Heathrow, so his claim is not supported. Then for part D, we have to estimate the number of days in July at Heathrow where the number of hours of sunshine is more than one standard deviation above the mean. So for part D, if I work out the mean plus one standard deviation, I've got 6.62 etc., which is what my calculator was displaying before, plus the 3.69 etc. And if I work this out, I get 10.32 etc. Now what do we need to do? We need to find out, going back to the question, the number of days in July at Heathrow where the number of hours of sunshine is more than one standard deviation above the mean. Now here we've been given information about the number of hours of sunshine each day, and we need to find out the number of days where the number of hours of sunshine is more than one standard deviation above the mean. Now the best way to do this is to draw a diagram. So if we draw a diagram, we have already information about the interval 8 to 11, and we know that this value we've just calculated is in between there. So we know between 8 and 11 is where this value lies. So let's just say it's over here somewhere. We've got 10.32 etc., which is this value here. So this value here is the 10.32 etc. And what we need to do is find out the number of days, so that is in between here. We'll call this D for number of days, and that's what we need to find out. And we know as well from 11 we've got an interval from 11 to 12 and then from 12 to 14. So here we've got 11 to 12 and then 12 to 14. And if I add those intervals on, we've got here 3 for the frequency between 11 and 12, and 2 for the frequency between 12 and 14. And we know that between 8 and 11, that frequency is 8. So, between the 8 and the 11, we have 8 for our frequency, and D is what we need to find out. So we can use linear interpolation to help us find out what D is. And if we were to use linear interpolation, we have 8 divided by the 11, take away 8, and that's equal to D divided by the 11, take away the 10.32, etc. And so the total number of days once we find out what D is will be this value plus the 3 plus the 2, because if we go back to the question, we're finding out the number of days in July where the number of hours of sunshine is more than one standard deviation above the mean. So, if we find out what D is, we have 8 divided by 11 take away 8, multiplied by 11 take away 10.32, which is 1.8, etc., which is 2 days approximately. And so, therefore, the total number of days will be this 2 plus the 3 plus the 2, which is 7. So we've got 7 days. Next, Helen models the number of hours of sunshine each day for the month of July at Heathrow by this normal distribution with parameters 6.6 and 3.72 squared. We have to use Helen's model to predict the number of days in July at Heathrow when the number of hours of sunshine is more than one standard deviation above the mean. If we let the random variable h equal the number of hours of sunshine, what we have is h following a normal distribution with parameters 6.6 and 3.7 squared. And what we need to do before we do anything else, if I go back to the question, is find out the probability that the number of hours of sunshine is more than one standard deviation above the mean, and then multiply that by the number of days in July to find out the number of days we have in total. So, with h following this normal distribution, we want to find out the probability that h is greater than the 10.32, one standard deviation above the mean. And so if we work this out, well, if we go to our calculator, and let's draw a diagram to help illustrate what we are working out. We've got 6.6, and then here we've got the 10.32, etc. And we are calculating this over here. So we've got an upper tail. So if we go to the distribution, and then we've got a normal CD, lower limit is 10.32, upper limit something really big, such as 1,000,000. Sigma is 3.7 and the mean is 6.6, and it turns out here we get 0.157, etc. And so what we would predict then is 31, which is the number of days in July, multiplied by this 0.157. So if I work this out, we get 4.87, etc. So we have 5 days. So for 5 days is where we would have the number of hours of sunshine being more than 1 standard deviation above the mean. So using our answers to part D and D, commenting on the suitability of the model, the 5 days from Helen is less than the 7 days, which we found earlier here. So the model, in this case, may not be suitable. Question number 2. A meteorologist believes that there is a relationship between the daily mean wind speed W kiloknots and the daily mean temperature T degrees C. A random sample of 9 consecutive days is taken from past records from a town in the UK in July, and the relevant data is given in the table below. So we've got T and W values, and the meteorologist calculated the product moment correlation coefficient for the 9 days and obtained R equals 0.609. For part A, we have to explain why a linear regression model based on these data is unreliable on a day when the mean temperature is 24 degrees. Well, if I take a look at the data here, what you can hopefully see is 24 degrees is outside the dataset. And so if we were to use the 24 degrees, we would require extrapolation, and therefore it's unreliable. And then for part B, we have to state what is measured by the product moment correlation coefficient. Well, in the context of this question, it represents the linear association between W and T. And then for part C of the question, stating your hypotheses clearly, we have to test at the 5% level of significance whether or not the product moment correlation coefficient of the population is greater than 0. So for part C, we've got H0, where rho is equal to 0, no correlation, and our alternate hypothesis H1, that's when rho is greater than 0, because we're testing whether the PMCC for the population is greater than 0. So if we draw a diagram, we've got our 0 value over here, and what we need to do is find out the critical region. So if I draw a diagram like this, we can find out what this critical region over here is. If we go to the tables, we are testing at the 5% level of significance, so that would represent the 0.05. Our sample size, if I go to the question, I've got 9 consecutive days. So where I have 9, that means my PMCC is 0.5822. So here I have 0.5822, and the value of R obtained is greater than this. That value of R is 0.609. So this is the value of R obtained. And so we're in the region where we reject H0, so because we reject H0, evidence to suggest that the PMCC is greater than 0. And then for part D, using the same 9 days, a location from the large dataset gave the mean of T being 27.2 and the mean of W being 3.5. And using the knowledge of the large dataset we have to suggest, giving a reason, the location that gave rise to these statistics. Well, we've got a high T value, but a low W. Now, a high T would suggest we are overseas, but a low W suggests we are not close to the sea. And therefore, the location could be Beijing. Question number 3. A machine cuts strips of metal to length L centimeters, where L is normally distributed with standard deviation 0.5 centimeters. Strips with length either less than 49 centimeters or greater than 50.75 centimeters cannot be used. And given that 2.5% of the cut length exceeds 50.98 centimeters, for part A we have to find the probability that a randomly chosen strip of metal can be used. Well, from the question we know that the standard deviation is 0.5. So we've got sigma being 0.5, and we are also told that the probability that L is greater than 50.98, that's equal to 0.025, 2.5%. So, if we draw a diagram such as the one we see here, here we've got our upper limit, which is 50.57, and 50.75, and here we've got the 49. And we want to find out this required probability. Now, before we do anything else, what we actually need to find is the mean. And for us to find out what the mean is, we would have to use the z values. And we know that z is equal to x subtract mu divided by sigma. And from this, we can find out what sigma is. Now, if I consider the probabilities over here and use the inverse normal, well, from the formula book, if I scroll down to the stats tables, we know from the stats tables where we have .0250 or 2.5%, that corresponds to a z value of 1.9600. And if we have our upper limit, we can find out what mu is. So, using this, we've got 50.98 subtract mu divided by sigma, which is 0.5. This is equal to 1.9600. And if we find out what mu is, mu is therefore equal to 50. So here we've got 50 for the mean. And now we are in a position to find the probability between 49 and 50.75. So the probability that L is in between 49 and 50.75, well, we can just use our calculator here. If we go to the distribution section, we've got a normal CD. Lower limit is 49, upper limit is 50.75, sigma is 0.5, mu is 50. So the required probability is 0.910 given to 3 significant figures. And then for part B, 10 strips of metal are selected at random. We have to find the probability that fewer than 4 of these strips cannot be used. Well, if we say that S is the number of strips that cannot be used, the probability of this is 1 minus the 0.910, etc. So, working this out, the probability that the number of strips for the strips that can't be used is 0.0895. Now, we need to be using a binomial because we've got a fixed number of trials. Each trial is independent of the other. So, if I say that S follows a binomial distribution with parameters 10 and 0.0895, etc., then we want the probability that S is less than 4, it says fewer than 4 strips, and that's the same as calculating the probability that S is less than or equal to 3. And if we calculate what this is, we go to the distribution submenu, we have a binomial CD, X here is 3, N is 10, P is this, so it turns out we get to 3 significant figures, 0.991. And then, for part C of the question, a second machine cuts strips of metal of length x centimeters where x is normally distributed with standard deviation 0.6 centimeters. A random sample of 15 strips cut by this second machine was found to have a mean of 50.4, have a mean length of 50.4 centimeters. And stating your hypothesis clearly and using a 1% level of significance, we have to test whether or not the mean length of all the strips cut by the second machine is greater than 50.1. So we are testing if the mean is greater than 50.1. So for part C, our null hypothesis, that's when the mean stays the same as 50.1, and our alternate hypothesis is when the mean, mu, is greater than 50.1. So essentially what we're doing here is we've got a sample and we're taking a mean of that sample. And for that, if we've got a sample mean distribution of size n, xn is normally distributed with parameters mu and sigma squared over n. So we know what sigma is, that's 0.6, and we also know that n is 15, we've got a sample of 15. So we have a normal distribution with parameters 50 0.1 and 0.6 squared over 15. Now, if we go to the formula book, we know for a random sample of n observations, from n being following from a normal distribution with parameters mu and sigma squared, x bar subtract mu over sigma over square root of n is normally distributed with parameters 0, 1. In other words, what we are saying here is z equals x bar subtract mu over sigma over square root of n. So if I find out the corresponding z value, z equals 50.4 subtract 50.1 divided by 0.6 divided by square root 15. So our z value is 1.936, etc. How does this help us? Well, if we were to draw a distribution like so, we've got 0 over here and the critical z value at, going back to the question, the critical z value is at 1%, so at 1% the z value is 2.3263. So here we've got 2.3263. The z value we just found over here is where z equals 1.936, etc. Rather, the z value we've just found is less than this at 1.936, etc. We're in the region where we do not reject h0. And because we do not reject h0, that there is insufficient evidence to suggest that the mean length of strips is greater than 50.1. Question number 4. We're given that the probability of A is 0.35, the probability of B is 0.45, and the probability of A and B is equal to 0.13. And for the first part of part A, we have to find the probability of not A given not B. Now, the best way to approach this question is to draw a Venn diagram. We've got events A and B, and we know that the probability of A and B is 0.13, and we know the probability of A is 0.35, so probability of A only, that's 0.35, subtract the 0.13, which is 0.22. So A only is 0.22, and the probability of B is 0.45, so the probability of B only is 0.32. And with this we can find the probability of not A and not B. The probability of not A and not B We know probability adds up to 1, so we've got 1 subtract 0.22, subtract 0.13, subtract 0.32. So if we work this out, it turns out we get 0.33. So we've got on the outside 0.33. Now, if we go to the formula book, what we need to do is use an adapted version of this formula here. And if we do that, well, what we'd have is the probability of not A given not B, which is exactly what we're finding. That's equal to the probability of not A and not B divided by the probability of not B. Now, if I find the probability of not B, that's the same as 1 minus the probability of B. So I've got 1 minus 0.45, which is 0.55. So now that I know the probability of not A and not B, and the probability of not B, I can therefore find the probability of not A given not B. So the probability of not A given not B, if I work out what this is, I've got not A and not B, so that's 0.33, divided by not B, which is 0.55, and it turns out here we get 0.6. Then for part B, we have to explain why the events A and B are not independent. Well, for independent events, we've got this condition: the probability of A and B is equal to the probability of A times the probability of B. So, let's write that down for part B as a condition. So, for independent events, the probability of A and B is equal to the probability A times the probability of B. So, the probability of A and B, that's 0.13. The probability of A times the probability of B, that's 0.35 times 0.45, which is 0.1575. And because these two are not equal, so the left hand side doesn't equal the right hand side in our condition, we can therefore conclude A and B are not independent. Now for part C, the event C has probability of C equaling 0.20. The events A and C are mutually exclusive, and the events B and C are statistically independent. And what we have to do is draw a Venn diagram to illustrate the events A, B and C, giving the probabilities for each region. Now here we've got a blank Venn diagram, and what we can do so far is fill in information about A and B. So we know A and B is 0.13. We know here we've got 0.22. And the reason the Venn diagram looks like this, we know A and C are mutually exclusive, which means they can't happen at the same time. And B and C are statistically independent, so B only will have a different probability to what we had before. Now, similar to what we mentioned here for independent events, the probability of B and C is equal to the probability of B times the probability of C. Now, if I go back to information given in the question, I know the probability of C is 0.20 and the probability of B is 0.45. And so therefore, the probability of B and C, that's equal to probability of B, which is 0.45, times the probability of C, which is 0.20, and if I multiply this together, I get 0.09. So, knowing that the probability of C is 0.20, C only will be 0.20 subtract 0.09, which is 0.11. And the probability of B only, well, if B is 0.45, that means 0.45 subtract 0.13 subtract 0.09 tells us what B only is, which is 0.23. So we've got 0.23. And so the probability on the outside region will be 1 minus the 0.22 minus the 0.13, subtract the 0.23, subtract the 0.09, subtract the 0.11. It turns out here we get 0.22. So now that we've got enough information, we have completed the Venn diagram. And now for part D of the question, we have to find the probability of B or C not included. So, the probability of B or C not included, well, that's everything that doesn't involve a B or a C. So that's this 0.22 and this 0.22 here, which is 0.44. So that's the required probability. Question number 5. A company sells seeds and claims that 55% of its pea seeds germinate. For part A, we have to write down why the company should not justify their claim by testing all the pea seeds they produce. Well, quite simply, the seeds would be destroyed in the process, so would have none to sell, which is why they can't use all of their seeds. Now, part B, a random selection of the pea seeds is planted in 10 trays with 24 seeds in each tray. Assuming that the company's claim is correct, we have to calculate the probability that in at least half of the trays 15 or more of the seeds germinate. Well, for part B, let S equal the number of seeds out of 24 that would germinate. Now, because we've got 24 trays, the probability that the seeds germinate is 0.55, that remains fixed. Each trial is independent of another, so we have here a binomial. S follows a binomial distribution with parameters 24 and 0.55. Now, in this question, we have a binomial within a binomial. Now, what do we know so far? We know so far that 15 or more of the seeds germinate, and we can use that to find out the probability for 10 trays that at least 15 germinate. So let's begin by finding out the probability that we have at least 15. So that's the probability of S being greater or equal to 15. So that is equal to 1 minus the probability that S is less than or equal to 14. So if I work out what this is, I've got 1 minus, and then if we go to the distribution sub-menu, we have a binomial CD. X here is X here is 14, N is 24, P is 0.55. So we've got 1 minus 0.700, etc. And if I work out what this is, I get 0.299, etc. So, how does this help us? Well, what we'll do now, we'll let t equal the number of trays with at least 15 germinating. So, we've got here a binomial distribution with parameters 10, we've got 10 trays, and probability that we have at least 15 germinating, that's 0.299, etc. And what we are looking for is us having more than half of the trays. So that means we are looking for the probability that t is greater or equal to 5. Because we want more than half. Half of the 10 is 5, we want more than this. So we have probability that t is greater or equal to 5, which is the same as 1 minus the probability that t is less than or equal to 4. So I've got 1 minus. Now if I go back to the distribution section, I've got a binomial CD. P is 0.299, x here is 4, n is 10. So I've got 1 minus 0.851, and if I work out what this is, I get 0.148 as my probability. Then for part C, we have to write down two conditions under which the normal distribution may be used as an approximation to the binomial distribution. So if we've got x following a binomial distribution with parameters n and p, and if n is large, so this is our first condition, n is large, and if our other condition, p is close to 0.5, if these two conditions are satisfied, then we can say x follows a normal distribution with parameters np and then np times by 1 minus p. So for part D then, a random sample of 240 pea seeds was planted and 100 of these seeds germinated, and assuming that the company's claim is correct, we have to use a normal approximation to find the probability that at least 150 pea seeds germinate. Well, first of all, what we need to do here is find out what NP is, and NP times by 1 minus P. And if I go to the formula book under the stats section, those came from here. So NP, that's equal to, well, I've got 240 seeds and the probability that they germinate is 0.55, so I've got NP equaling 240 times 0.55, which is 132, and NP times by 1 minus P, I've got 240 times by 0.55 times by 1 minus 0.55, which is 59.4. Now let's say that x follows a normal distribution with parameters 132 and variance 59.4. What we need to do here is use the normal approximations. So we have at least 150 seeds germinating, so with our normal approximation we are looking for probability x is greater or equal to 149.5. So what we've done over here is apply a continuity correction. So if I calculate this, well, let's just draw on a quick normal curve, like so. We've got our mean being 132, and here we've got the 149.5. We're calculating this probability. So if I calculate that, if I go to the distribution section, I've got a normal CD. Lower limit is 149.5. Upper limit is something really big, such as 1,000,000. Sigma is equal to the square root of 59.4. Then we've got 132 here. So it turns out we get 0.000015, etc. Now for part E of the question, using our answer to part D, we have to comment on whether or not the proportion of the company's pea seeds that germinate is different from the company's claim of 55%. Well, the probability we've just found here is very small. The 0.0155, etc. is a really small probability compared to the 55%, and so therefore the claim is incorrect. Question number 6. At time t seconds, where t is greater or equal to 0, a particle p moves so that its acceleration a meters per second squared is given by a equals 5t I minus 15t to the half j. When t equals 0, the velocity of p is 20 I meters per second. We have to find the speed of p when t equals 4. What we need to do to begin with is find out what v is. V is equal to the integral of the acceleration with respect to time. So we need to integrate with respect to time 5t I minus 15 t to the power of 1/2 j with respect to t. And if I work out what this is, we have 5/2 multiplied by t squared. This is in the I component, and in the j component we've got minus 10t to the power of 3/2. And then we add on some constant of integration c. Now we are told that when t equals 0, the velocity is 20I. So when t equals 0, velocity is equal to 20I. So I've got v, which is 20I. That's equal to, well, here I have 0 I subtract 0 j plus c, and it turns out then the vector c is equal to 20I. And so therefore the velocity will be given by, well, in terms of the i's, I've got 5/2t squared plus 20 and in terms of the j's, I've got minus 10 t to the power of 3/2. This is what the velocity is equal to. So now when t equals 4, velocity, that's equal to 5/2 times 4 squared plus 20, and then I subtract 10 times by 4 to the power of 3/2 j. So it turns out the velocity when t equals 4 is 60I minus 80j. we need to find the speed. So the speed is given by the magnitude of the velocity. So the magnitude of the velocity is equal to 60 squared plus negative 80 squared, and then square rooted. So it turns out we have 100 meters per second when t equals 4. So when t equals 4, the speed is 100 meters per second. Question number 7. A rough plane is inclined to the horizontal at an angle alpha, where tan alpha equals 3/4. A particle of mass m is placed on the plane and then projected up a line of greatest slope of the plane. The coefficient of friction between the particle and the plane is mu. The particle moves up the plane with constant deceleration 4g/5. For part A, we have to find the value of mu. Well, first of all, if we know that tan alpha is equal to 3/4, we can form a right angle triangle. The hypotenuse is 5, that's the square root of 4 squared plus 3 squared. And so sine alpha is 3/5 and cos alpha is 4/5, just in case we need them later on. So for part A, let's begin by drawing a diagram. We've got our particle, it moves up the slope with constant deceleration 4g/5, which is why we've got the negative. We've got the reaction force, we've got friction acting in the opposite direction of where the particle is travelling up, and then we've got the weight. Now, if we resolve parallel, then to the slope we've got minus f minus mg sine alpha, and that's equal to the mass times by the deceleration, so that's f equals ma. So we've got minus 4/5 mg. And if we resolve perpendicular to the slope, we have r equals mg cos alpha. And we also know that f is equal to mu multiplied by r. So if I call this one, this equation 2, and this equation 3, then what we have is minus f, so that will be minus, and then f is mu r, and r is mg cos alpha, so we have minus mg cos alpha minus mg sine alpha, and that's equal to minus, and then rather we multiply this by mu, because we've got mu times by r, and that's equal to minus 4/5 mg. Now the mg's cancel everywhere, so I'm left with minus mu cos alpha minus sine alpha equals minus 4/5. And if I substitute in the values of cos alpha and sine alpha, and recognizing that the minuses cancel everywhere, I've got mu times by 4/5 plus 3/5, and that's equal to 4/5. And if I solve for mu, we can see mu is equal to 1/4. And then for part B, the particle comes to rest at the point A on the plane. We have to determine whether the particle will remain at A, carefully justifying our answer. Well, there's no acceleration, and that's because the particle comes to rest. Now, what we'll do is we'll see what the frictional force is equal to and what the weight force is equal to. And then we can compare them to determine whether the particle moves or not, see if one outweighs the other. So, if we concentrate on the frictional force, we know that that's minus mu mg cos alpha. So, working this out, I've got minus, well I know what mu is, that's 1/4 times by, well we'll leave the m at the end, but times this by 9.8, and then times by cos alpha, which is 4/5, and then we times this by m. So it turns out the frictional force is minus 1.96 m. For the weight force, we've got minus mg sine alpha. So I've got minus 9.8, that's what g is, times by 3/5, that's what sine alpha is, times by m. So here I get minus 5.88 m. So what we can see then is the weight force, which is minus 5.88 m, has more of an influence on the particle than the frictional force, which is minus 1.96 m. So the magnitude of the weight force is greater than the magnitude of the frictional force. And so what we can conclude from this then is the particle does not move. Question number 8. Now in this question, I and j are horizontal unit vectors due east and due north respectively. A radio controlled model boat is placed on the surface of a large pond. The boat is modelled as a particle. At time t equals 0, the boat is at a fixed point O and is moving due north with speed 0.6 meters per second. Relative to O, the position vector of the boat at time t seconds is r. At time t equals 15, the velocity of the boat is 10.5 I minus 0.9 j meters per second. The acceleration of the boat is constant, and for part A, we have to show that the acceleration of the boat is 0.7 I minus 0.1 j meters per second squared. Well, for this question, we would have to use the Suva equations because we've got constant acceleration. Now, we've been given a time, we're finding out the acceleration, we've been given an initial velocity and a final velocity, so it makes sense for us to use v equals u plus at. So for part A, if we use v equals u plus at, we have 10.5 I minus 0.9 j, and that's equal to, well, it's moving with speed 0.6 meters per second, and that's when it's moving due north. So due north is when it's moving in the j direction, because j is due north. So we add on, well, this is equal to 0.6 j plus 15 a. We've got the time 15, and the acceleration is what we're finding. 15a, that's equal to 10.5 I minus 1.5 j, and if I divide through by 15, we can therefore conclude that the acceleration is 0.7 I minus 0.1 j meters per second squared. Then for part B, we have to find r in terms of t. Well, for this, we have to use s equals ut plus a half at squared. This time, s, we're going to write r instead. So for part B, using r equals ut plus 1/2 at squared, I've got r equals u, which is 0.6 j, and I multiply this by t, and then I add on 1/2 times by 0.7 I minus 0.1 j times t squared, and the units are meters. So we can conclude then r is equal to, well, in terms of the j's, I've got, well, in terms of the i's, I've got 0.35 of them. And in terms of the j's, I've got 0.60 minus 0.05 t squared j, and the units are meters. Then for part C, we have to find the value of t when the boat is northeast of O. Well, if I think about north, east, south and west, when it's moving northeast, if here I've got the j component and if here I've got the I component, then northeast would imply that I equals j. So northeast implies I equals j. So I've got my I component, 0.35 t squared, and that's equal to my j component, which is 0.6 t minus 0.05 t squared. So I can gather everything over to one side, leaving me with 0.4 t squared minus 0.6 t, and that's equal to 0. Factorize out a 0.2, so I've got 0.2 t times 2t minus 3, that's equal to 0. So we get from here t is either equal to 0 or 1.5, and so therefore t is equal to 1.5 seconds when it's moving northeast. And now we have to find the value of t when the boat is moving in a northeast direction. Well, here, let's think about using v equals u plus at to find a general velocity vector for v. V is equal to 0.6j plus 0.7 I minus 0.1 j multiplied by t meters per second. So in general, v is equal to 0.7 t I, and we add on 0.6 minus 0.1 t j. Again, similar to before, we know that northeast would imply that I is equal to j. So we have the I component 0.70, and that's equal to the j component 0.6 minus 0.1 t. 0.8 t is equal to 0.6. That means t is equal to 0.75 seconds. Question number 9. A uniform ladder AB of length 2A and weight W has its end A on rough horizontal ground. The coefficient of friction between the ladder and the ground is 1/4. The end B of the ladder is resting against a smooth vertical wall as shown in figure 1. A builder of weight 7W stands on top of the ladder. To stop the ladder from slipping, the builder's assistant applies a horizontal force of magnitude P to the ladder at A towards the wall. The force acts in a direction which is perpendicular to the wall. The ladder rests in equilibrium in a vertical plane perpendicular to the wall and makes an angle alpha with the horizontal ground where tan alpha equals 5/2. The builder is modelled as a particle and the ladder is modelled as a uniform rod. For part A, we have to show that the reaction of the wall on the ladder at B has magnitude 3W. Now, if I take a look at my diagram, I can add the weight force on to begin with. And for the weight force, we've got the weight of the ladder being W, and it acts in the centre. What we also have is a builder who's got a weight of 7W and he stands on top of the ladder. So here somewhere is the builder. He stands on top of the ladder and his weight is 7W. So we've got 7W acting down, and we know that the wall is smooth, so there's no friction, and would have a normal reaction perpendicular to the wall. So our normal reaction is over here. We'll call this normal reaction S for now. Now, on the bottom of the ladder, we know that the ground is rough, so we've got friction opposing it, and we've got a force of P towards the wall. That's what we were told in the question. The builder's assistant applies a horizontal force of magnitude P to the ladder at A towards the wall, and this force is perpendicular to the wall. We also have the reaction over here, we'll call it R, and what we'd also have is the assistant over here. So there is my assistant. So when we come to show that the reaction of the wall on the ladder at B has magnitude 3W, the way we can approach this is to take moments about A. And the reason we want to take moments about A is because that will eliminate all the forces here. So for part A, if I take moments about A, then I've got W times by the perpendicular length, which is A cos alpha. So I've got W A cos alpha, and I've also got 7W multiplied by 2A cos alpha, which is the perpendicular length. So I've got here 7W multiplied by 2A cos alpha, and that's equal to the forces going in the other direction. We've got S multiplied by 2A sine alpha. So I have S times by 2A sine alpha. So if I tidy this up, I've got W cos alpha plus 14W cos alpha, and that's equal to 2s sine alpha. So we've got 15w cos alpha equals 2s sine alpha. And if I divide through by sine alpha, that means we have, rather, if I divide through by cos alpha, that means I've got 15w equals 2s times by tan alpha. And I know what tan alpha is, that's 5 over 2. So I've got 15w equals 2s times by 5 over 2. So I've got 15w equals 5s, and so therefore s equals 3w. That's exactly what I wanted to show. And then for part B, we have to find in terms of w the range of possible values of p for which the ladder remains in equilibrium. So for us to find the possible values of p for which the ladder remains in equilibrium, well, if I draw my ladder here, and then I've got the wall, so here is my wall, and here I've got my ladder, there's two situations which we need to consider. We've got the situation where the ladder, for it to remain in equilibrium, we've got our assistant over here, and what he's doing is he's pushing the ladder this way, and if he's pushing the ladder that way, he's pushing it with a force of P, and that's to prevent it slipping. And then what we have over here then is friction opposing it because the ladder is moving this way. So that's the first situation. And for the second situation, if we copy and paste this, we could have a situation whereby we've got our assistant at the bottom over here, where the assistant is putting so much force in that the ladder ends up like this. So the ladder is moving in towards the left, and in that case friction would act this way instead. So what we're talking about in this question, when we come to find a range of possible values for p, we've got the situation whereby we've got F acting this way, or we could have F acting in this way instead. So it depends on which way the ladder moves. It could, the ladder, if here is our original ladder, the ladder could move this way, in which case it's moving away from the wall from here, or we've got the ladder ending up over here, so it moves inwards and the friction opposes it this way. So we have to think about those two situations. So before we do anything else, what we can do is actually find out what the reaction force R is. We've got W plus this 7W, and essentially what we're going to be using is F equals mu R. So for part B, if we consider the vertical motion, well, certainly we've got R equals W plus 7W, which is 8W. Now, if we consider what the friction force is, friction, that's equal to mu r. So I've got mu 1/4 times by 8w. So here I get 2w for the friction force. So there's two situations as I was discussing for P. We could either have a maximum force or a minimum force, and that just depends on which way F is pointing. So for the maximum, I have S and F acting in the same way and P opposing it. So P max, that will equal S plus F. So I know what S is, that's 3W, plus F, which I just said is 2W. So here I get 5W for the maximum force of P. I could also have a minimum, and that's when S and F are in opposite directions. So the difference between them, we have 3W, take away 2W, which is just W. And so the range of values for which we could have P, that will be W less than or equal to P less than or equal to 5W. Now for part C, often in practice the builder's assistant will simply stand on the bottom of the ladder. We have to explain briefly how this helps to stop the ladder from slipping. Well, first thing we need to think about is R would increase with the builder on top of the ladder. That's because we've got his weight plus the weight of the actual builder. So we've got assistant plus builder, that'll give a really big value of R, and that's if we resolve vertically upwards. So that's the first thing we need to think about. And then, if we take moments about A just as we did previously, the normal reaction at B would remain unchanged, and that normal reaction is S. So if we work through all the calculations once again and think about how we would find friction, well, this time, if we increase R, this would also increase the maximum value of F, because if I think about F equals mu R, if I increase R, that means I increase F. So increasing R would increase the maximum F. Question number 10. A boy throws a stone with speed u meters per second from a point O at the top of a vertical cliff. The point O is 18 meters above sea level. The stone is thrown at an angle alpha above the horizontal where tan alpha equals 3/4. The stone hits the sea at the point S, which is a horizontal distance of 36 meters from the foot of the cliff as shown in figure 2. The stone is modelled as a particle moving freely under gravity with g equaling 10, and for part A we have to find the value of u. Now in this question we have to use the Suva equations because we've got constant acceleration, and for projectile motion we will be using S equals ut plus a half at squared. So for part A, if we use S equals ut plus 1/2 at squared, then if we consider the horizontal motion with A equaling 0, because we've got no acceleration horizontally, the equation reduces down to S equals ut. So I've got the horizontal distance, which is 36 meters, and that's equal to u cos alpha. And can we find out what cos alpha is? Well, if I know that tan alpha is 3/4, then I can form a right angle triangle. I've got a 3, 4, 5 triangle. Sin alpha then is 3/5, cos alpha is 4/5, and tan alpha is 3/4. So with this, if I know that cos alpha is 3/5, that means I've got 36 equals u multiplied by 4/5 multiplied by t. And so therefore, ut is equal to 45. We'll call this equation 1 for now. And if I resolve vertically, then I know vertically that O is 18 meters above sea level, so the displacement will be negative 18, and that's equal to, well, the vertical component, that's going to equal u sine alpha. So I've got u sine alpha multiplied by t minus a half times by g, which is 10, times by t squared. So I've got minus 18 equals u times by 3/5 times by t minus 5t squared. So I've got minus 18 equals 3/5 ut minus 5t squared. So I'll call this equation 2. So what I need to do now is substitute 1 into 2. So if I substitute in 1 into 2, that will eliminate the ut's, leaving me with minus 18 equals 3/5 times by 45 minus 5t squared. And if I rearrange, 5t squared is 45, t squared is 9, so therefore t is equal to 3. And if I call this equation 3, I can substitute in equation 3 into equation 1. So I've got 45, which is equal to ut, so I've got 3u. And so therefore, u is equal to 15 meters per second. Now for part B, the speed of the stone when it is 10.8 meters above sea level will give you answer to 2 significant figures. So we need to find out what this speed is. So the way we will approach this is to recognize, well, if I'm 10.8 meters above sea level, that means up to here somewhere, I've got 10.8, which means here I would have 7.2. And that's because the 10.8 plus the 7.2 gives the 18. And what I need to do is find out the speed at this point. We'll call it v meters per second. So here I've got v meters per second. And what I can do essentially is split this up into its horizontal and vertical components, and doing so will allow me to find out the speed using Pythagoras. Now, the formula we will be using, if I go back to the kinematics formula, I will be using v squared equals u squared plus 2as. So, for part B of the question, if we use v squared equals u squared plus 2as, then vertically, I've got v vertical equals u vertical plus 2as. So I've got u sine alpha squared plus 2 times negative 10 times by s, which is negative 7.2. It's the displacement. If I take this to be the 0 level, then my displacement will be negative 7.2 because I'm finding the speed 10.8 meters above sea level. And knowing that sine alpha is 3/5, I've got 15, which is u, times by 3/5 squared plus this term here. And if I work this out, I get 225. And so therefore, the vertical component is equal to 15 meters per second. So if I go back to my diagram, the vertical component is 15 meters per second. And I can do a similar thing horizontally to find out the horizontal component. So if I consider the horizontal moment, I've got A equaling 0, which would imply that my equation would reduce to V horizontal squared equals U horizontal squared. So I've got V horizontal squared equals U cos alpha squared. So I've got U times by, well, I know what U is, that's 15. So I've got 15 times by 4/5 squared, which is equal to 144. So V horizontal is 12 meters per second. So if I go back to my diagram, I've got 12 meters per second here. And so therefore, I can find out the value of V. That's equal to V vertical squared plus V horizontal squared, and then I square root. So if I square root, I've got 12 squared plus 15 squared, and then this is square rooted. It turns out, if I work this out, I get 19 point, well, I'll just get 19 meters per second given to two significant figures. And that's what I wanted to find out. Now, for part C, we have to suggest two improvements that could be made to the model. Well, we could use a more accurate value of G, that's the first suggestion, and the other suggestion we could include air resistance.